In this video, we'll discuss the OLS estimator. The OLS estimator is a way of estimating the coefficients in a linear regression model. So the usual way of introducing the OLS estimator is graphically through a series of pictures. What I do here is something different. So the problem with the pictures is that they seem very intuitive at first, but actually they don't teach you a lot about why the OLS estimator works. So they give you a false sense that you have understood something when really you haven't. So I'll try something different here, a very econometric and I think very modern approach, but then we also get to the pictures, so you'll get both. We start by writing down a regression model for an outcome variable, y. And here I'll just do two regressors to keep the notation simple, but this will generalize to any number of regressors. So y is given by beta naught plus beta 1 x1 plus beta 2 x2 plus an unobserved component or error term u. And saying that we can write down the production process like this is actually an assumption that we made. It was called the functional form assumption. If you're just getting started with econometrics and all you've seen are linear models, then you may think that this functional form is the only reasonable functional form. That's actually far from true. This form can actually be quite restrictive, and it is something that you have to defend on grounds of your insight into the economic environment that you're studying. The next assumption that we adapted was that we assumed that the conditional expectation of the error term given the regressors is 0. We call this the extraneity assumption. This assumption says that we cannot predict the level of u from information contained in the regressors. The extraneity assumption is far from innocuous, and indeed it is often very difficult to defend in practice. And the reason for this is as follows. Remember that u gives the combined effect of all the x's that we don't observe. The problem is that all the x's, that is the observed ones as well as the unobserved ones, arise from the same economic system, and therefore they are often connected in logical ways. Suppose that we are investigating exam scores as a function of study time and other variables, and u would contain unobserved variables, for example, ability. Now it is quite natural to assume that students with low ability may be motivated to study more because they want to make sure that they at least pass the exam. Therefore, there's a natural relationship between u and x1 that we can exploit to predict u from x1 and x2. In that case, the extraneity assumption would not be satisfied. Let's assume that we are studying in an economic environment where both the functional form assumption and the extraneity assumption are plausible. What is the conditional expectation of y, the outcome variable, given x1 and x2? In other words, what we're trying to do is we're trying to predict the outcome from information contained in the regressors. What is the best way to predict y from x1 and x2, assuming that we have a complete and correct understanding of the data generating process? Well, to predict y, we have to predict the regression curve plus the unobserved component or error term. Now, under the extraneity assumption, actually we cannot predict u from x1 and x2, so we would predict a 0 for this part. This means that to predict y, we just have to predict the regression curve. But the regression curve is a function of x1 and x2, and we were assuming that we have this information. We also assume that we have a full understanding of the data generating process, that is, we know the betas. So we can predict the regression curve precisely, and then to predict y from x1 and x2, we just predict the true regression curve. When writing down the regression curve here, I've written the betas in red ink, and that's because I want you to pay special attention to the betas. The betas parameterize our functional form. That is, if we know the betas, then we understand our production process. And in particular, we can use the slope coefficients to compute ceteris paribus causal effects. And that's what we're interested in. We have shown that under our assumptions, the regression curve is a best prediction of the outcome given the information contained in the axis. What is a best prediction? A best prediction has very low prediction error, and we have chosen to measure prediction error by a mean squared criterion. Let's evaluate the mean squared prediction error at this best prediction. So we're taking the outcome and we are predicting it by the regression curve. The prediction error is the difference between the two. We then square the difference and take the expectation. This is the prediction error of the best prediction. For this prediction to be actually a best prediction, it has to be better than any other prediction. We can generate other predictions by combining x1 and x2 in other ways than this one, and this could be possibly nonlinear ways, but let's just think about other combinations that are linear combinations of x1 and x2. This best prediction is a linear rule, and it has to be better than any other linear rule. Being better means that it has smaller prediction error than the prediction error from any other linear rule. So let's just write down the prediction error from some other linear rule. So this is the prediction error of an arbitrary linear prediction. This inequality says that if we choose a linear prediction rule where the coefficients of the prediction rule corresponds to the betas from our economic model, then we get a lower prediction error than we get by choosing any other linear prediction rule. We can use this inequality to redefine our betas. And remember, we are really interested in these betas. And in particular, we can define these betas as the coefficients beta 0, beta 1, and beta 2 that minimize the prediction error of a linear rule. So we're saying we just want to minimize this guy. And we are wondering how should we choose the b's to achieve the minimum. So we're looking for the argmin. And this inequality here tells us that the argmin is achieved by our betas. Actually, that is not quite correct, because here we have a weak inequality. So that says that the betas give a linear prediction rule that is at least as good as any other linear prediction rule. So this leaves the possibility that there's some other linear prediction rule that works equally well. To make sure that our betas give the unique best prediction rule, we need an additional assumption, and that was our full rank assumption. The full rank assumption makes sure that the best linear prediction rule is unique. So what do we have here? On the left-hand side, we have the beta coefficients that we're interested in. These coefficients describe economic behavior, and if we know these coefficients, we can compute causal effects. On the right-hand side, we have the random variables y, x1, and x2. These random variables describe our population and observed facets of our population. There is no u here. We are summarizing the joint distribution of these three variables by taking an expectation. So this is an average over the population. If we had full knowledge of the joint distribution of y, x1 and x2, then we could figure out this right-hand side, and by this equality sign, this would allow us to figure out the coefficients that we're interested in. Such results, where we re-express parameters of interest as a function of the population distribution, are what econometricians call identification results. Before we continue, let's back up a little and let's remind ourselves of what econometrics is. We're doing econometrics because we're interested in learning about reality. We want to learn about the economy or the society that we are part of. There are economic models that explain economic behavior that apply to a wide range of economies. So the tricky part is, in what kind of economy do we live? Unfortunately, our economy is producing data. We can use this data by applying statistical methods to figure out in what kind of economy we live, and this allows us to understand economic behavior. So to do econometrics, we combine economic models with statistical methods, and the statistical methods handle the data part. But now you will notice that we haven't really talked about data so far. We've only had 3 assumptions: the blue functional form assumption, the yellow exogeneity assumption, and the purple full rank assumption. These assumptions don't involve data, they are purely about economic behavior. In other words, so far we've only done this part of econometrics. The reason now that we need statistics is that actually we don't know the joint distribution of y and the axis. This is where statistics comes in. It allows us to figure out this part. To do statistics, we need data, so let's assume that we can draw a random sample. In the sample, we observe y, x1, and x2. Our observations are indexed by I, and we'll assume that we have n observations. Now, using this data, we want to estimate this population quantity, and we'll do that by following the principle of the method of moments. To do that, we replace the population random variables y, x1, and x2 by their sample counterparts, and we replace the expectation over the population distribution by a sample average. So we'll just take this here, and now we replace population quantities by the sample counterparts. Instead of the expectation, we have a sample average. By solving this minimization problem for the data that we observe in the sample, we get optimal coefficient values, and we'll call these beta naught hat, beta 1 hat, and beta 2 hat. These beta hats are called the OLS estimator. And OLS is short for ordinary least squares. Beta naught through beta 2 solve the minimization problem for the population, and the population is fixed, so they will always be the same and they are just numbers. The OLS estimator solves a minimization problem that depends on the sample that we observe. Since the sample is random, then so will be the OLS estimator. Let's again recall our characterization of what econometrics is. It consists of economic modeling and statistical methods. To develop this expression and interpret the economic meaning of these coefficient values, we relied exclusively on economic modeling. Now, this here is an estimator of these coefficients. To assess how accurately our estimators measure our parameters of interest, we have to dig into statistics. This page motivates the OLS estimation strategy, and it also gives you a pretty good blueprint for how econometrics works. We have economic identification arguments and then statistical estimation theory. In this derivation of the OLS estimator, I have emphasized that we have to derive this expression. And the reason that this is so important is that to derive this expression, we're making assumptions about the economic environment. So we as economists who want to apply empirical methods have to assess the plausibility of these assumptions in the economic environment that we are studying. Once we have this expression, we can use it somehow to produce an estimator. And now all that we are interested in is how does this estimator relate to the values that we are estimating. What happens here, the exact mechanics of this, is not really something that we are interested in as econometricians. Funny enough, this is actually the exact opposite of how people thought about OLS historically. So people were thinking about this problem even before the idea of a regression problem in the background existed. And even today, many introductory statistics classes introduce OLS by talking a lot about this really kind of uninteresting and irrelevant problem. So we do that as well, just for completeness. And we do this in the context of regression with a single regressor. When we fit a regression with one regressor, we are estimating an intercept and one slope coefficient. We are estimating them by solving this minimization problem. Now here, to make things a little easier, I'll write the sample average here in sum notation. This expression reads as follows. We take B0, B1. Those are candidate values for beta naught hat and beta 1 hat. Now we'll take the regression curve that would prevail if B0 and B1 were our correct coefficient values. And we evaluate this hypothetical regression curve for each observation I at the x that we observe. This gives us this here. And now we look at the difference between that value and the observed outcome. We square this difference and then take the average square. Let's illustrate this mechanism in a graph. For every observation, we have an observed x value and an observed y value. Let's suppose that we have only n equal 2 observation and 1 is down here. That means y1 is here, x1 is here, and our second observation is up here, so that y2 is here and x2 is here. Choosing B0 and B1 corresponds to choosing a linear curve, and changing B0 will change the location of the curve, and changing B1 will change the tilt of the curve. Let's suppose that we start with this hypothetical regression curve. Let's evaluate this expression for I equal 1. First thing we want to do is we want to find this value on the hypothetical regression curve. To do that, we'll just find x1, and then we read of the value of this curve. That is, we'll find the y value corresponding to this point. Next, this difference here corresponds to the vertical difference between our data point and the point on the regression curve that we just found. Finally, we can represent this square in the formula by the area of this square in our graph. We can draw a similar square for the observation I equal 2. We draw as many squares as we have observations, and then this criterion here will be the average area of a square. To find the least squares estimates, we evaluate this criterion or this objective function for different potential regression curves. That is, we moving around this curve and evaluating the criterion, and then we'll try to find the curve that makes the criterion as small as possible. Or in other words, we'll try to find the curve that makes the average area of a square as small as possible, and that's why it's called least squares, because we want to make the squares as small as possible. The optimal curve is also called the fitted regression curve. What does the fitted regression curve look like? If we have only 2 data points, then we can fit a linear curve directly through these 2 points. With this curve, the area of the squares corresponding to the 2 data points will be 0. So the average area of a square will be 0, and this is the minimal value that we can ever hope to achieve. So this will be optimal with 2 data points. However, if we have more than 2 data points, then it is typically not possible to fit a linear curve such that all the data points lie directly on the curve. Instead, OLS tends to fit a curve such that most of the data points lie kind of close to the curve, but typically no data points lie directly on the curve. The reason why this is happening is that the square here in the criterion is convex, and that means that it penalizes large distances more than it does small distances. So it's better to have many small distances rather than have some distances be exactly 0 at the cost of having some really large distances. A nice feature of the fitted regression curve is that it is very intuitive to the human eye, so it is very close to the curve that we would fit if we had to fit a curve by hand. Once we have found the fitted regression curve, we can read off the intercept by looking at the point where the fitted regression curve intersects the vertical axis. This is the estimated intercept, beta hat naught, and I'm writing omega naught to indicate that this is an estimate and not an estimator. It's an estimate because it's the value of the estimator that we obtain if we observe this particular data set. To read off the realized value of beta hat 1, we can look at a 1-step increase in the horizontal direction and then read off the corresponding vertical increase in the regression curve. This will be the estimate of the slope coefficient. If you want to fit an OLS regression with more than just one regressor, then this works conceptually exactly the same way, except now instead of fitting a curve through a point cloud in a 2-dimensional space, you're fitting a curve through a point cloud in a 3, 4, or even higher dimensional space. So it's much more difficult to visualize, but conceptually it's the same. In practice, when you run an OLS regression, that is when you apply the OLS estimator to actual data, you don't have to solve this minimization problem manually. Instead, you will have a statistical software package such as Data or R compute the OLS estimates for you. Therefore, you don't really have to worry much how this optimization problem is solved numerically. Still, for the special case of OLS regression with just one regressor, I'll give you a formula to compute the estimated slope coefficient beta 1 hat. In this course, we'll use that formula sometimes to illustrate some mechanisms. However, you will never ever apply this formula in econometric practice. beta 1 hat can be computed by dividing the sample covariance between the outcome and the regressor by the sample variance of the regressor. Using this formula, you can compute the value for beta 1 hat on any given sample. Now let's rewrite this formula a little bit. To do that, we'll define sigma hat y squared equal to the sample variance of y, and we'll define sigma hat x1 squared equal to the sample variance of x1. Now I want to rewrite this part here, and I will use that the variance here is equal to sigma hat x1 times sigma hat x1. So if I multiply these two, I'll get the square, right? So I get the variance, so that actually this inequality holds. This here is equal to this. Now I also want to divide by sigma hat y, and because I want to maintain the inequality, if I divide by it, I also have to multiply by it. This expression scales the covariance between y and x1 by the standard deviation of y and x1. This scaled version of the covariance has a name, and it's called a correlation coefficient. I'll call it rho hat y x1, and this is also known as Pearson's correlation coefficient. The interpretation of the correlation coefficient is exactly the same as for the variance, and the difference is that its value is bounded between -1 and 1. So if the correlation coefficient takes the value 0, then there is no correlation between the variables y and x1. If it takes the value -1, then there's perfect negative correlation between the variables y and x1. And if it takes the value 1, then there's perfect positive correlation between the variables y and x1. In summary, we can compute beta 1 hat by taking a correlation measure and scaling it by a positive number. So beta 1 hat is essentially just a way of measuring the strength of a correlation. We've already discussed that the sign and magnitude of a correlation does not necessarily reflect the sign or the magnitude of a causal effect. This is our first hint that an OLS regression with just one regressor will often not estimate the causal effect that we are interested in. Let me summarize briefly what I discussed in this video. In this video, I derived the OLS estimator. I did that in 2 steps. First, I derived an identification result. To derive this result, I combined our assumptions about functional form, exogeneity, and full rank. These are all economic assumptions and have to be justified from our understanding of the economic environment. The identification result gives us a new way of writing our coefficients of interest. We want to use data from a random sample to estimate these coefficients, and that is a statistical problem. We apply the method of moments and derive an estimator that is called the OLS estimator. The OLS estimator gives us a recipe for computing estimates on every possible sample. These estimates are supposed to recover our parameters of interest. How well this works is something that we'll discuss when we'll discuss the statistical properties of the OLS estimator. We'll never have to implement this recipe ourselves. We have statistical software to do that. Still, for the special case of OLS with one regressor, I gave you some graphical intuition of how this recipe works. Also, for the case of OLS with one regressor, I explained that the slope coefficient beta 1 hat is a way of measuring a correlation.